Lesson number 2, group activities. In this case, we've got graphs of the races run by these 4 zombies. Let's analyze just a little bit here. We'll take a look at hertz. We are given that the distance is here on the vertical axis and time is there on the horizontal axis. And so if I wanted to analyze, for example, this point at the top right, that tells me that the distance traveled is 5 somethings. In this case, it's miles. So that's a 5-mile race. And then if we go this way to the horizontal axis, then the time is also 5, in this case 5 hours. So 5-mile race in 5 hours. So I think we've answered question 1. What distance was the race? It was 5 miles. Who won the race? So if you take a look at each picture, you'll see that they all got to that 5-mile mark at exactly 5 hours. And so in this case, it was a 4-way tie. What was the average velocity of each zombie over the course of the race? Okay, so here's a formula that you know. Average velocity is the change in distance over the change in time. And for each of our 4 zombies, the change in distance was 5 miles. And then the change in time was 5 hours. They all took exactly the same amount of time to cover those 5 miles. And so we can reduce this and we get 1 mile per hour, or 1 mph. What was the average velocity of each zombie over the first 2 hours? Okay, so here we finally got some variation. So in the first 2 hours, let's look at this first top left graph, Feynman. So 2 hours in, that's this spot right here. So we're going to go up to the graph and get to this spot. So we've got 2 hours in, and it took, and went 2 miles in 2 hours. And so the average velocity there, this person went 2 miles in 2 hours. And so 1 mile per hour. That makes sense actually, because that's just Feynman's distance graph is just a line. So his velocity was constantly 1 mile per hour the whole time. But now let's take a look at hertz. Again, going 2 hours in. So there's the 2-hour mark. And we're going to go up to the graph and put a dot right here at the 2-hour mark. And now we have to do some estimating. We're going to estimate this number right here. I don't know, 0.7, 0.8, something like that. And so for hertz, average velocity is the change in distance, which I'm saying is 0.7 miles, divided by the change in time, 2 hours for every part of this problem. So 0.35 miles per hour, much slower than Feynman's average velocity in the 2 hours, first 2 hours. Okay, same deal for Noether and Planck. Let's do them real quick. So 2 hours in here and 2 hours in here. And so then again, we need to estimate these numbers. So let's estimate here, maybe 3.2-ish. And here, looks like about in the middle, 2.5. It's okay if you don't have exactly the same numbers as me. So average velocity here, 3.2 miles over the course of 2 hours. So 1.6 miles per hour. That's the fastest average velocity we've seen in the first 2 hours. And then here, in this case, about 2.5 miles in 2 hours, or 1.25 miles per hour. Okay, so let's just fill in those answers here in number 4. Okay, so I've just copied our 4 calculations from the previous page. Moving on to number 5, when was Noether running the fastest? How can you tell? Okay, let's take a look at the graph for Noether. So that's this lower left. So when was she running the fastest? Well, what we're looking for is, what her average velocity was over different periods of time. So in the beginning, she was covering a lot of ground in a short period of time. And at the end, she was covering, that was, I don't know, let's call that like a third of an hour, quarter of an hour. And in the last quarter of an hour, she covered hardly any distance. You can see in the last quarter of an hour, maybe she only got from this bottom arrow to the top arrow, not very much distance. But in the first quarter of an hour, she got from there to 1 mile. And so when was she running the fastest? Well, she was running the fastest when this graph is as steep as possible, and this graph gets less and less steep as time passes. Therefore, she was running the fastest at the start of the race. At the start of the race, since that's where her graph is steepest. Okay, number 6, explain in detail Planck's running strategy. When was he running fastest? When was he running slowest? Okay, so taking a look at Planck's graph, it's the most complicated one. So you can see the graph is quite steep in the beginning. That means that Planck was running very fast in the beginning. And then the graph slows down. And in fact, you can see that the graph is pretty much horizontal for about an hour there. And so if the distance is not changing, the distance stays 2.5 miles for this whole hour in here, that means that Planck isn't moving at all. And then after taking a rest, he starts to run slowly and then faster, faster, and faster, sprinting at the finish. So let's write that. Okay, so we sprint, and then jog, and then rest, and then we jog, and then we sprint again. That's the running strategy. So when was he running fastest? That was at the beginning and also at the end. T equals 0 hours and T equals 5 hours. When was he running the slowest? Well, there was a time in there where it looked like he wasn't running at all. He was just sitting, maybe snacking on some brains. So that looked like it was between T equals 2 to 3, say, where he wasn't moving at all. Okay, number 7, a radar gun was pointed at each zombie right at the instant where T equals 3. Devise a strategy for estimating how fast Feynman and Northrop were going at that instant and explain. We want numerical final answers. Okay, so let's take a look at Feynman first. So Feynman is this top left graph. T equals 3 is right here. And we want to know the velocity at that instant, not over the period of 2 hours or an hour, but at that one moment in time. Well, this one's easy because Feynman's velocity is constant. It is always 1 mile per hour every place during his race. So no calculus needed for that one. So for Feynman, his velocity instantaneous is exactly 1 mile per hour. Piece of cake. But for Noether, it's not so easy. So let's take a look at Noether's T equals 3 moment. So T equals 3 is right here. And we want to know how fast she was running at that exact moment in time. Okay, so what we could do is take a look at her average velocity between, for example, T equals 3 and T equals 2. We could just calculate the average velocity there. Or we could calculate the average velocity between, say, T equals 3 and T equals 2.5, a smaller window, and that would give us a more accurate answer. Or maybe we go T equals 3 and T equals 2.8, something like that. And so this is kind of the idea. It's a fundamental calculus idea, is that calculating instantaneous velocity is really hard. And so instead we're going to do an average velocity, but over a really, really tiny time window. This should kind of remind us of what we were looking at with that soccer goal from the first class, where we look at the person's foot, but not over a long period of time, rather just a teeny tiny time interval containing the moment of contact with the ball. So let's unclutter the picture here. And I'll say that, that another option would be to say that the Noether's velocity at that one moment, T equals 3, is probably not that different from her average velocity, say between, let's see if we can pick another color, purple, say between 2 and 4. So we could go to T equals 2 and we could go to T equals 4, and we could calculate the average velocity on that interval. and say that on that interval, her velocity isn't changing very much. I guess she's slowing down just slightly on that interval, but probably not that much to make a difference. So at t equals 2, we've already got the point plotted here, and we estimated that was a distance of 3.2. So let's still now go and estimate at t equals 4. So I'll call that, I don't know, 4.5, I guess. And so if we want to calculate the instantaneous velocity, so 4.5 and 3.2. Here we go. Instantaneous velocity at t equals 3 is roughly equal to her average velocity on the interval 2 hours to 4 hours. And we're estimating this as, again, change in distance over change in time. So let's take a look at our numbers again. Change in distance, 4.5 to 3.2. 4.5 minus 3.2, and then the change in time, well, at the end was 4 hours, and at the beginning was 2 hours. So we calculate here, 1.3 divided by 2, 4.65 miles per hour. Again, it's okay to get answers that are a little bit off from my answer, but it shouldn't be too far off. Not to say my answer is perfect, it isn't. But we should get something near there. Now, there are other ways to think about answering that question, and we will tackle some of those, or at least one of those, in the demo, which is coming up.